Hello everyone, welcome to my YouTube channel. So in this lecture, I will teach about the insertion and elimination reaction in the organometallics chemistry. So oxidative addition and the substitution allow us to assemble one electron and two electron ligands on the metal. So with insertion, its reverse reaction, elimination, we can now combine and transform this ligand within the coordination sphere, ultimately expel this transform ligand to form the free organic compound. So that means in the oxidative addition or the substitution reaction, the new ligand is connected to the metal center, but in the insertion reaction, the combination of the ligand within the metallic within the complex framework happen that will help to forming the new organic compound. So in the insertion, a coordinated two electron ligand A11B can insert itself into an MX bond to give MABX, where ABX is a new one electron ligand in which a bond has been formed between A, B, and both M and X. So here A double bond B is a ligand which insert between the MX bond to form this compound. So here new ABX is a new one electron ligand which is where the new MA and BX bond is formed. So there are two types of insertion reaction. One is this, one is to 1, 1, 1, and one is 1 to insertion. So in which metal and X ligand end up the bond to the same or adjacent atom of an L-type ligand. So here, so 1:1 here, this is the example of 1:1 microserry insertion reaction. So here the MX is inserted into the between the here X is inserted into the C atom. So where the CX bond is formed. So here it is a 1:1 insertion. So this is 1:1. This is 1:1. This is 1:1 insertion. And this is the example of 1:2 insertion. Here the X is inserted in this CX bond to form this new CCX bond. So here this 1, 1, 1, 2. So here X is inserted into the adjacent carbon. So this is a example of 1:2 insertion. So for example, the CO gives only 1:1 insertion, that is both M and X group end up attached to the CO carbon. So this is the example of 1:1 insertion. On the other hand, the ethylene gives only 1:2 insertion in which the M and X end up the adjacent atom. What is the 2 electron ligand? So in general, nita-1 ligand give 1:1 insertion and nita-2 ligands give 1:2 insertion. So SO2 is the only common ligand that can give both types of insertion as a ligand, and SO2 can be nita-1 and nita-2. So that means the nita-1 ligands, but that which is the monodentate ligand. So that means the CO, nitrile, isonitrile, or phosphine, that will give 1:1 insertion ligand, and on the the nita-2 ligand like the H2 or the alkyl, that will give the 1:2 insertion in the organometallic chemistry. So in principle, insertion reaction are reversible, but just as we say for oxidative addition reactive elimination, for many ligand only one of the two possible direction is observed in practice, or probably because this direction is strongly favored thermodynamically. So like the reactive elimination and the oxidative addition, insertion and the elimination reaction is reversible, but thermodynamics play the crucial role. Which direction that will be favored. So ligands only on the so for example, SO2 commonly insert into the MR bond to give alkyl sulfonate complex, but this rarely eliminate SO2. So conversely, diazoirin complex readily eliminate N2, but N2 not yet observed to insert the metal aryl bond. So that means here the insertion reaction occurs. So SO2 it inserted between the MR bond to form this metal sulfonate complex. So that is only insertion, no elimination occurs. So SO2 does not elimination from this complex. So here this no equilibrium in the left direction. So that is a totally right direction reaction. So it is the formation of the MSO2 is kinetically favorable. So that is a one direction process. And another case where the N double bond AR is eliminated to from this MR and N2. N2 do not insert between the M and AR bond. So that also in the directed in one direction. So the ligand the which direction the reaction will occur, that will depend on the ligand. So here the thermodynamics play a crucial role. So that insertion will occur or the elimination will occur. So the immediate precursor to the final insertion product usually has both 1 electron, 2 electron ligand coordinated. This means that the need 3 electron set of ligand is converted to 1 electron insertion product. So that a 2 electron vacant site is generated by the insertion. So in the insertion reaction, a 1 electron ligand, that means the X type ligand, is inserted into the 2 electron ligand, L type ligand. So electron net means not 3 electron ligands is converted into a 1 electron insertion product. So upon the insertion, there is a 2 electron vacant site is generated upon the insertion. So here X is a 1 electron ligand and CO is a 2 electron ligand. So upon the insertion in the M into X, this acyl ligand framework is generated. So here it is also a X type ligand. So here 1 electron ligand. So here total 3 electron system converted to 1 electron system and 1 vacant site is generated. So this site can be occupied by the external 2 electron ligand and insertion product is trapped. So conversely, elimination requires the vacant site, so that an electron complex will not undergo the reaction unless a ligand first associate. The insertion also requires a cis arrangement of the 1 electron 2 electron ligands, where the elements is generated a cis arrangement from this ligand. So the formal oxidation state does not change during the reaction. So that means in the both case, that means in the insertion reaction will happen only with when the both X and L type will in the cis arrangement, and also for the elimination case, then when the generate cis, when these two ligands will in the cis arrangement also, that time also the elimination reaction will happen, and the oxidation state during this change of the elimination, this external elimination reaction is 0 and electron count is -2. So on way to picture the insertion reaction is consider the X ligand migrates with this MX bonding electrons to attack the faster orbital of a double bond ligand. So 1 here the summary, 1 insertion occurs with this neta-1 bound ligand such as CO, and 1,2 ligand insertion occurs with the neta-2 bound ligand such as CH2. So next I will discuss about the reaction involving the CO. So CO shows a strong tendency to insert into the metal alkyl bonds to give metal acyl. The reaction has been carefully studied for a number of systems, although the details may follow the pattern set by the best case known case. So here the metal CO molecule a strong tendency to insert in the metal alkyl bond to form this metal acyl. So here the MnCO4 CO5 Me, here the CO is inserted between this Mn Me bond to form this metal acyl, and another molecule of CO is attacked to form this MnCO5, the acyl this acyl intermediate. So the mechanism of the migratory insertion applies in many cases. The alkyl group. So mechanism of the migratory insertion reaction applied in many cases. The alkyl group in the reagent undergo migratory insertion in the CO to the given acyl intermediate. Thus is trapped by the added ligand L to give the current product. So here in this reagent MnCO whole 5 MECO. So here Me inserted to the C bond to form this acyl intermediate. It one bracket side is formed. Another L ligand will connect to form this final product. So the kinetic in this situation are reminiscent of the dissociative substitution. Expect that the two electron side is formed at the metal in the migratory step, not loss of the ligand. So using the usual steady state method, the rate is given by so here the rate one is the K1 and K minus 1, and here is the K2. So using the steady state method, the rate is equal to minus d reagent by dt, that is K1 K2 L reagent minus plus K1 minus plus K2. So these are the all three regimes, all of which are found in real cases. So the rate is dependent if the K minus 1 is very small relative to the K2L, the K2L. So here this is very small in K2L. So K2L cancel, L cancel the equation reduces to the rate equal to K1 regime. So because the K1 is very small, the L always trap the intermediate. That means the rate of the overall reaction is governed by the K1, and we have the first order reaction. So that means in first case when this inverse reactions rate is very small, that case the always this L-type ligand will connected to this molecule to from this final product. So that time so only the rate is depend on the this reaction rate constant of this first reaction. So if and second case, if K minus 1 is very large relative to K2L, then the equation becomes rate equal to minus d reagent by dt is equal to K and K2 L reagent by K1. So in this case, the intermediate almost always goes back to starting reagent, and the second step is the attack by L governed by the overall rate. So we have the second order kinetic. So when this reaction order rate is very fast, that time this second step is not possible. So here it goes back to this one, and here the overall rate of the reaction is dependent on also K1 and K2. That is the second order reaction. So if K1 is comparable to K2, so that situation is more complicated, and the equation is usually rate equal to minus d reagent by dt equal to K observed reagent. That K observed where K1 K2L by K1 minus K2. So in this case, the intermediate is trapped by L and a rate that is comparable to reverse migration. So this is the handle by the plotting K observation versus KL. In such case, the intercept 1 by K1 and slope dividing the slope of the intercept keep K minus K2. That is still the intermediate partition between the forward rate and backward reaction. So when the incoming ligand is 13 CO, the product contains only one 11 CO, so which is fixed to the newly formed acyl group. So this shows that the methyl group migrated to the coordinated CO rather than the free CO, attacking the MnCO bond. So that means in the Doudrine level experiment, when 13 CO is inserted used in the upcoming ligand, so also that case only the one level CO, the newly metal complex contains only one metal CO. So this so that the methyl group migrated to the coordinated CO rather than the free CO. So any stereochemistry at the alkyl carbon is written in this insertion as is constituted the mechanism. So here the stereochemistry of the methyl group is written in the insertion reaction. So we can tell here the level CO is located at the product because there is a characteristic strip of new CO stating the lower energy in the higher spectrum of the complex as a result a greater mass of 13C cross normal carbon. So that by studying the reverse reaction elimination of CO from 13 M1 where we can easily label an acyl carbon of the 13C, we find that the levels end up in the CO Cs to the methyl. That this is an example of the general strategy if you examine the reverse reaction to learn something about the forward process. MnCO5, where MCO to form these intermediates, to form this. If this elimination occurred, so here this CO and Me is in the cis position. So if the acyl carbon is labeled with 13C, so we found that the end of the CO cis to the methyl group. So this level 13 and MO is a cis position. So this is example of the general strategy. We need to examine the reverse of the reaction and learn something about the forward process. So this relies on the microscopic reversibility, according to which the forward and reverse reaction of the thermal process must follow the same path. So in this case, if the level CO ends up with the cis to Me, the CO to which the methyl group migrates in the forward reaction must also be in cis to methyl. So we are fortunate in the seeing the kinetics part of this reaction. If a subsequent scaling of CO had been fast, we could have detected nothing. So that means according to the microscopic reversibility, the forwarded and backward reaction should follow the same process. So here in this 13C scaling reaction, 13C reacts when the in both forwarded and reverse, both in insertion reaction, the CO and Me is the cis position. Also in the elimination reaction, the acyl group where the CO eliminate from in acyl group, that will be cis position. So that will confirmed by the leveling experiment. So that will truly follow the microscopic reversibility of these two reactions. So it is also possible to use the reversibility argument to show the acyl ligand in the product is bound to cis to the original methyl rather than the anywhere else. So we did this work. CO elimination is CO with the level is cis to acyl group. If the acyl CO migrates during the elimination, then the methyl in the product will stay where it is and so remain cis to the level. So if the methyl migrates, then it will be end up both cis and turns to the level. So that is observed. So here, if Me or CO moves, if the methylene migrates, so then this Me is both cis to the level and normal. If the CO moves, so if acyl CO migrate during the elimination, then the methyl in the final bar will stay. That is so remain cis to level. So here, if the methyl moves, that will also if the two possibility for methyl moves, if the methyl moves, so that is maybe cis to the level CO or maybe here a trans to the level CO. If CO moves, so in both cases the methyl is cis to the level CO. So this observation is that the methyl also migrates when the reaction is carried out in the direction of insertion. The cis MECO whole code required for this experiment can be prepared the photolytic method. And we again use the aspector to tell where the level has gone in the product. So this is only the feature of migratory insertion of any MnCO whole code that does not reliable carry over to other system where the product acyl is occasionally found at the site originally occupied by the alkyl. So next we will discuss about the changing the insertion rate. So the steric bulk in the ligand set the accelerate insertion. So no doubt because the acetyl is the product occupying one potential site is far less bulky than the alkyl and carbonyl occupying two sites. So in the starting complex LNMCO, so Lewis acid such as AlCl3 or H+ can increase the rate of the migration insertion by such 10⁸ fold. So metal acyl are the more basic at oxygen than are the corresponding carbonyl by virtue of the resonance. So by the binding to the oxygen, the Lewis acid will expect the tabloids or transition state and steering on the trapping the L and therefore speed up the reaction. Polar solvents are also excellent to significant exchange rate. So a rate of this insertion reaction also may increase by the using the polar solvent or the Lewis acids such as LCl3 or H+. So another important way to promoting the reaction is the oxidation of the metal. So CO2 FeM is normally very slow to insert, but on electron oxidation at -70 degrees is methyl isonitrile using selenium 4 salt gives the acyl in which the solvent has played the role of the incoming reagent. So as we saw, complex can be very labile, but another factor here may be the increase the electrophilicity of the metal, leading to the larger partial positive charge on CO carbon. So migratory insertion of any minus to the electrodeficient CO carbon seems to be good this description of the CO insertion. So the rate of the reaction may be increased in the response to the increase of the delta positive charge on the CO carbon. So oxidation will also speed up the trapping by the phosphine, but this may no longer the redetermined step. So here using the oxidant that will increase the electrophilicity of the metal. So about the oxidation, the electrophilicity of the metal will positively increase. That will increase the delta positive charge on the CO carbon. That will help to facilitate the insertion reaction. So under CO, trityl cation PH3C plus can catalyze the migratory insertion in the complex such as CpCO2 FeMe by oxidation to CpCO2 FeMe dot. So these 17 electron radical cation then undergo migratory insertion with CO as the incoming ligand, and the trityl radical from in the first step then reduce your 7 electron insertion product to 8 electron CpCO2 FeCOMe and the starting trityl cation. So the rate of the insertion are also increased to some extent by using more nucleophilic solvent, suggesting that a solvent may act as a temporary ligand to stabilize the initial solvented insertion product. So here this cation will oxidize the metal complex to form this cation radical intermediate. So that will reduce to the this radical to 70 electron insertion product to the 18 electron inserted product. So here also the nucleophilic solvent also stabilized this intermediate to accelerate the rate of the reaction. So early metals are Lewis acid in their own right, tend to bind the oxygen ligand. They therefore accelerate their own Lewis acid and catalyzed for the reaction. The product anti-acyl as shown in the follow. So here this unlimited zirconia also speed up the insertion because these type of metal are the Lewis acidic in nature. So here the migratory insertion will adapt to form this anti-acyl product. So by altering the thermodynamic in favor of the adduct, this effect is even sufficient to promote normally unfavorable CO insertion into MH bond as shown CP star. The insertion reaction will form this and unfavorable MH bond insertion to MH bond. So in this case, the formation of the intermediate carbonyl complex is proposed for zirconium to sodium as both pyrosis, and these intermediates must be very unstable. And limited back bonding should take the MO such that relative toward the insertion. So next we will discuss the apparent insertion. So this can in fact go by the entirely different route, and the late metal alkoxide in unstable and the Me group dissociated as MeO minus to give in the ion pair with two electron vacant site at the metal. The free CO present then binds to the reactor site and strongly activated toward the nucleophilic attack at the CO carbon owing to the positive charge on the metal. The product is inserting metal ester complex. So here OMe metal alkoxide is very unstable, so that will eliminate to form this cationic intermediate. Then this nucleophilic will attack the electron deficient carbon center to form this ester intermediate. So genuine migratory insertion into the MO bonds are also possible. The MEO DPP CO insertion into PT OME bond, where for NIMEO CO insertion to the NIME bond is followed from third bond. For NI, the ME bond is significantly stronger than the OME bond. But the migratory insertion with the NME is migratory paper owing to the weaker CO bonds of the alkoxy carbonic for platinum. NME OME bonds are equally strong to the stronger methoxy carbonic CO bond result in the direction of the MOME bond. So next we will discuss the double insertion. So given that the methyl groups migrate to the CO to stop there, why does the resulting acyl group not migrate to another CO to keep the CO ligand? So if migratory migration happen rapidly, we might even get the unknown ReCO MLN polymer, a material that is believed to be thermodynamically unstable in respect to the CO itself. The complex that have been formed in the double insertion can be made by independent route from this MoCOCl and MoCO5. It is easily eliminated to CO, give this MECO, MnCO5. We suggested the double insertion is thermodynamically unstable with respect to the MECO, MnCO5. The CHO and the CF3 group share with this MECOCO the property of the eliminating CO irreversible to give the hydride and trifluoromethyl complex respectively. This reason is again probably thermodynamic because the MCOMe and the MH and MCF3 bonds are distinctly stronger than the MCH3. The bond formed in the CO elimination of the acetyl. In contrast, the isonityl do undergo repeated migration insertion to give the polymers with as many 100 isoniazide until inserted. So that means, so upon the one time of MECO insertion to the form this acyl, that will also from another CO insertion to form this MECOCO bond, but this MECOCO is a double insertion product is very unstable. That will eliminate the CO to form again this MECOCO ligand. And but for the isonityl case, the double insertion occur and that with many 100 isoniazide inserted. So this is the example. The products that appear to rise the double migratory insertion of CO have been found by the Yamamoto in the following reaction, where the RH2NH COAR PD catalyst to form this R2N COCO-AR. So in fact, the reaction goes via a cycle, so in which the reductive elimination, not a migratory insertion from this R2COCO-AR carbon-carbon bond. In the first step, the oxidative addition ARI forms a palladium AR bond. The ARCO ligand is then formed by the conventional migratory insertion, and the R2CO group arises by the nucleophilic R2H on the second CO. So here the mechanism where the first the ARX is oxidative additive to form this ARPDALX2, then the CO migratory inserted to form this ARCO mode, then another CO attack to form this intermediate, then the nucleophilic attack of the R2CA on this CO moiety on this one, then the double insertion body animated to form this active state. So this is a classical example of the double insertion product. So isonitriles, next we discuss about the insertion product of the isonitriles. So isonitriles insert very readily into the MR bond, even MH bond, to give this immunoside, which can be neutral bound for the early metals or in metal cluster. So here CP3U isonitride is bound to from this to be inserted to this metal and R bond to form this CP3U CR inner. There also the isonitride is bound to the metal hydride bond to form this intermediate. So next we will discuss the insertion involved with alkene. So alkenes will give one product. The insertion coordinated alkenes into the MH bond is very important reaction because it gives this alkyne a constitution is a key step in variety of catalytic reaction. So alkene, including alkyl polymerization, perhaps most commonly important organometallic reaction. As neutral to ligands, alkene give on to insertion. So this is the reverse of the familiar beta elimination reaction. Some insertion reaction are known to give agostic rather than the classical alkyls. This is probably lie on the path of insertion into the MH bond. The position of the equilibrium is decided by the thermodynamics of the particular system that depends strongly on the alkene. For simple alkenes such as ethylene, equilibrium tends to lie to the left, but for the alkenes with electron withdrawing ligands, the alkyl is particularly stable and the equilibrium will lie entirely to the right. So alkyls such as electron withdrawing function have the MCO bond that are particularly strong, and the alkyl are stable enough to have the beta hydrogen. So here this alkene in inserted with the metal hydride to form this agostic interaction intermediate to form this alkyl intermediate. So here the platinum PR3 and the CH2 X or H or F to form this on to inserted product. Here alkyne inserted to the metal hydride to form this metal alkene species. That this alkene in inserted to metal deuterium to form this intermediate. So then the CH2 bond is rotated. And this so this equation strategy for the Fincher and co-workers have been used to determine the mode of the APDH addition to the unsymmetrical cis alkene. So on the isomerization of the transform, the deuterium is incorporated in the insertion step, is written by the substrate. So labels the beta carbon of the product. The mode of insertion is constant the PD hydride acts as a hydride in nature. So here, so usually the stoichiochemistry of the insertion is a seen. So here the alkene is inserted in the seen manner where the palladium is a plus delta positive charge and hydrogen minus delta negative charge, and this carbon is delta negative. This was from here this inserted product is happened. But the initial from cis vinyl alcohol is the celestial electron can sometimes reagent to the trans isomer and it to vinyl. This can lose the anti-addition of the variety of XH group. So here this intervinyl group that will form the trans-alkene product. So as we saw for the CO insertion and elimination, 2 electron vacant site is generated by the insertion. Reversible insertion and elimination equilibrium also known. The vacant site may be filled by the any suitable ligand such as solvent, excess alkene, or agostic CH1 or phosphine. So here the R3SN is the silicon hydride bond is inserted. So from this metal hydride species, then this alkyne inserted to form this inserted into the silicon SR3. So from this alkene intermediate, this it isomerized to give this cis intermediate. The reductive elimination occurred to form this final product. So in this case, the molybdenum CP2 alkene hydride. Here, upon the inserted of the metal hydride to the alkene, where the vacancy is formed, that is trapped by the PRC group to form this intermediate. So the transition state. So the transition state for the insertion has been essentially coplanar in COCH arrangement. And this implies that the both insertion and elimination also require the NCCH system to be capable of becoming coplanar. So we have seen how we can stabilize the alkyl against the beta hydride elimination by having the non-coplanar NMCH system. The same principle to apply to stabilize the alkene hydride complex. So it under the compound 7.5 undergo insertion at least 14 times more rapidly than the 7.6. Although the alkene MHRC is both case, only 7% non-coplanar MCCH bond arrangement. So one application of the alkene insertion is the hydrozirconiation of the alkene by CP2HCl. The terminal alkenes extend the anti-Marconi direction to give the stable 1 degree alkyne. The internal alkene such as 2-butene insert to give the unstable 2 degree alkyne, which is not observed. This intermediate beta elemented to give the 1,2-butene, and the 1-butene can also give stable 1 degree alkyne. The observed product, which is particularly not to the reaction because the terminal alkene is less stable than the internal alkene. The insertion goes in the way it does because of the 1 degree alkyne is automatically more stable than the 2 degree alkyne, probably for the steric degree. So 1 degree alkyl can now be maximized in a number of ways. So here the butene 1 inserted to the metal hydride to form this stable 1 degree alkyl. But in case of the 2-butene, so here this 2 degree alkyl is formed, which is the unstable, which is upon eliminated beta elimination to form this butene, then again it is helped to form this alkyl 1 degree alkyl intermediate. So insertion into MH versus MR bond. So we saw in the last section that there are thermodynamic reason CO insertion generally takes place into the MR bond, not in MH bond. So the alkene insertion in contrast is common for the MH bond, but less common for MR bond. So alkyl polymerization is the reaction that will repeated alkene insertion into the MR bond. So thermodynamics will favor the reaction with MR bond. So it is comparatively that must be due to the kinetic factor. Burkhardt and Korkas have compared the barrier for insertion of the ethylene into MR bond where the R equal to H or ET, M equal to ruthenium or cover. The reaction among the MH has the 16 electron lower barrier. This corresponds to the migratory aptitude K by KET equal to 10 to the power 6 as you seen. Before reaction involving the MH are almost always kinetically more facile than reaction of the MR bond. So this means that the alkene probably has the best steric kinetic facility for the insertion than does the CO. So looking at the reverse reaction elimination, we see that this implies that beta elimination in the alkyl will have kinetically very much easier than the beta alkyl elimination. It will also give a thermodynamically more stable product, so it is not a surprising that beta alkyl elimination is extremely rare. In those cases where it is observed, there is always some special factor that modified the thermodynamic for both. For example, F metal MR bond appear to be comparatively instead stronger than MH bond, so both beta hydride elimination and beta alkyl elimination can be observed. So here the beta alkyl elimination from this molecule or beta hydride from this molecule. So the stain or the presence of electronegative substitute on alkene are moving to the alkyne and has some other factors that can cause the thermodynamic and the kinetic in favor. So here the alkyne is inserted to the metal alkyl bond As in case of the ethylene inserted in the MR bond, also described by the Bergman, the insertion mechanism also confirmed by the labeling scheme. So inserted into the MM bond is shown in this picture, where this CO complex in the L upon elimination of L, the ethylene was coordinated, then inserted to the CD3 molecule, then upon the beta hydride elimination to form this alkene, then upon reacting of CD3 to form this intermediate. The styrene can insert into the MM bond of ROCHOAP2. Initially, homolysis give the metallose radical RHOAP, which adds to the alkene to give PHCOCH2. Then the also incident that the ROAP photopolymerization to increase the intermediate C radical and repeatedly acrylate where they recombine the metallo radical. So then we will discuss the insertion of the dienes. So as in seen, butadiene and allene can react with a variety of hydride by the one-point insertion. By the butadiene also react with the metal hydride to give the apparent one-point insertion product. Since this ethylated hydride also not vacant side, the CO dissociation is slow. Intermediate indirect mechanism must be operating. This is thought to be by the H-atom transfer. If one diethyl allyl radical, this is subsequently trapped by the metal. Only the cost of the physically stable radical. So here the butadiene from this metal radical and this radical that we will select from this final product. So alternative CO and alkene insertion, a series of cation and butadiene catalysis such as then is known to the co-primation to CO with the alkene such as ethylene to get sterically alternative copolymer. The polymer is interesting from the particle standpoint because it's the carbonyl functionality so leads to itself to useful chemical modification. The polymerization reaction also for the mechanistic interest because of the especially perfect alternation of the alkene or CO insertion being. So here the palladium where the ethylene pointed to the metals of metal insertion and again co-polymerization to this intermediate. Of phosphine mineralization, double insertion is forbidden for the thermodynamic reasons. The double alkene insertion is very rare because of the high affinity to the catalyst for CO together with the mass towards the. So in summary, the alkyl normally migrates to CO position as the first step in the CO insertion. Alkene insertion the catalyst over into the image versus MR bond. So thank you.